All right, so getting started on our today's lecture, I want to do a quick review on what we covered last lecture. Right, so the first lecture, remember, we're talking about basic terms in thermodynamics, like what is the system, what is the surrounding, what are the kind of walls we are, what kind of equilibrium we're describing when we're talking about thermodynamic equilibriums. And then in our Monday lecture, we spent time talking about the ideal gas law. So basically, we first look at the ideal gases, and then talking about how do scientists derive the ideal gas law, or namely, how does the pressure, volume, temperature, number of mole of ideal gases, connect to each other, right? So how do you predict the behavior to come up to PV equals nRT? We then generalize our conclusion in ideal gas law into equation of state. That is, for any specific system that we care about, there will always exist an equation of state that describes pressure, volume, temperature, and the amount of substances. Or you can describe volume as a function of pressure, temperature, number of moles of different substances in that system. All right, so that's the equation of state. Now, state function is something else that Dr. Wu will introduce you in our next lecture. So do not connect these two terms. Equation of state, it's a function that describes the relationship of these macroscopic properties, volume, pressure, temperature, etc. And then to further generalize this observation, we want to use the mathematical tools to see how many experiments are needed for scientists to determine the equation of state of an unknown system. So that's when we did a series of partial differential equations to show that for three variables, if we are considering the molar volume, pressure, and temperature, keeping the number of substance unchanged, we effectively only need two independent partial differential equations in order to derive what the equation of state is. And those two partial differential equations, we give them names as thermal expansivity or cubic expansion coefficient. So that's alpha as a function of temperature and pressure. That's 1 over molar volume. Partial differential equation of molar volume versus temperature, constant pressure. And the isothermal compressibility chi, which is a function of Tp. So that measures the change of volume with respect to pressure at constant temperature. All right, so these are just general properties or general experiments scientists can set up in order to derive for the equation of state. Now, some of the simple example you can see in the textbook, like to calculate alpha and chi for ideal gases. So that should be very straightforward to calculate. Or on the more complicated end, I want to show you what's the biggest or most complicated math we will encounter in this entire quarter using the Van der Waals gas equation as an example. That is, given the Van der Waals equation of state for real gases, which is showing here, can you express the thermal expansivity, which is alpha? Can you solve alpha for Van der Waals gases? That's as complicated as our math will become. So that means we'll do the derivation together. And if you're comfortable following every step I'm doing, you're probably good to go on the math end. If you don't understand anything, it's not because your math is not good enough. It's all about thermodynamics. If you feel challenging following what I'm doing in this derivation, this is a good hint for you to go back and review your calculus and get familiar with the tools of calculus from here. All right, so let's do this. So this one have two different ways to solve it, as we said. One, we can use the cyclic chain rule. Two, you can do the derivation on both ends with respect to temperature. And why that is the case? Now, the thing is, when we're setting up this kind of calculation, you observe what we're looking for. So in this case, we're looking for alpha, which is the thermal expansivity. And you look at it, we're looking at a partial differential equation of molar volume with respect to temperature while keeping pressure as a constant. So if we want to directly solve it, we're facing an obvious problem because in the original Van der Waals equation, we cannot simply express molar volume as a function of temperature and pressure. You have to solve a quadratic equation which is way more complicated than it should be. So this is why we say like, oh, we can use the cyclic chain rule, or we can take differential on both ends with respect to temperature. So we get that dVm over dt term. All right, so both ways will give you the same result. I'm gonna work with you on the cyclic chain rule approach. So follow me and also like try the other approach yourself and check to see if we get the same answer. All right, cyclic chain rule. So what is cyclic chain rule? Again, we have three different variables. We have Vm, temperature, and pressure. Right, so writing it out, we're looking at the Vm over dt at constant P, and then dt over dP at constant Vm times dP over dVm at constant temperature. And that gives you -1. All right, just writing out the equation, but now with the thermodynamic terms instead of x, y, and z. Now if we observe what we're looking for here, the dVm over dt at constant P, so that's the partial differential equation we need in order to solve for alpha, but we don't have a way to express dVm over dt. But we do have a way to express like temperature as a function of pressure, or pressure as a function of temperature and Vm. Right? So let's look at this one first. So in this case, in order to solve this partial differential equation, we want to express temperature as a function of pressure and Vm. So going back to the Van der Waals equation, do we have a way to do it? Well, we just move that r to the left, and it's pretty straightforward. So we can write temperature as P plus A over Vm squared times Vm minus P over constant r. Right? Express temperature as a function of P and Vm. And in here, we're trying to solve temperature as a function of pressure while keeping Vm as a constant. So in this entire equation, we only have one pressure here. This term doesn't have any pressure dependence, so we don't have to worry about it. So that means we can solve like dt over dP at constant Vm to be just like Vm minus B over R. But we only have like one pressure over here. So this is a simple differential equation. It's like solving, well, dAx over dx gives you the constant. So 50% done. And then we look at the second part. Now here we want to express pressure as a function of Vm and T. So again, looking at the equation, well, we only have one pressure term. So what is pressure? So P equals to RT over Vm minus B and minus A over Vm squared. Am I doing that right? Yeah, right. So moving that Vm over minus B to the right-hand side and minus the A minus A over Vm squared. And we're trying to solve the dP over dVm. So the calculus we're trying to use is dx to the power of n. D over dx gives you nx to the n minus 1. So that's the basic calculus equation we're using. So in order to solve it here, we got dP over dVm at constant t. Now on the left-hand side, we have Vm minus B, that's on the bottom. So that becomes negative RT, and then Vm minus B to the square. And here we have Vm squared on the bottom, so that becomes 2A Vm cubed. Pretty straightforward calculus, just using this one calculus rule. All right. And then we have, well, this part is done. This part is done. We have a way to express what we want, which is a partial differential of Vm over T at constant P. So that's, well, dVm over dt at constant P times this first term, which is Vm minus B over R, and then the second term here. minus RT over Vm minus B to the square plus 2A Vn cubed. And this entire thing gives you -1. All right. And then moving the terms to the right, we have an expression of your dVm over dt at constant p. So this one just moving everything to the right. That's the negative r over Vm minus b and times, well, there's everything on the bottom. Negative RT Vm minus b squared plus 2A Vm cubed. And then just organizing the terms by multiply, like say, my negative Vm cubed and Vm minus b on both bottom and top. Clean it up. Let's see, negative Vm cubed. This becomes r Vm cubed times Vm minus b. On the bottom we have RT Vm cubed minus 2A Vm minus b to the square. It takes a little practice. You don't have to do it right now, but it's just moving terms around. And then we have our partial differential equations. Obviously, the next step is alpha, which you divide this entire partial differential equation by a Vm term, and you get alpha equals to 1 over Vm times the dVm over dt at constant p. Let's see, r Vm squared Vm minus b RT Vm cubed minus 2A times Vm minus b squared. Yes?
I was wondering for this class, when it comes to cyclic chain rule, will we always be able to like find 2 of the 3 differentiations?
I'll make sure it's solvable for you. Let's put it this way. Like, if you ever encounter a scenario, like you feel like you have to solve a quadratic equation and then do the partial differential equations, there's probably easier way to do it.
Okay. So we're doing all of this because we can't isolate Vm on the left-hand side from the van der Waals equation?
Yeah, you can only get the Vm as a function of t and p by solving the quadratic equation. That's too complicated. So this is like a shortcut. That's a calculus shortcut. All right. And if you look at the math itself is actually pretty straightforward. It's just because we're dealing with these fundamentally complicated equation and expression that make it look horrible. That's all. All right, and there is a different way to solve it, and it will give you the same answer. And that's one of the nice things about this class, is you can solve the same problem using 2, 3 different approaches, and you'll always get the same answer, so you can check it on yourself. Okay, any questions before we move on? Yes?
For the second method of like solving for this, would you say like it's any like easier?
Well, yes and no. So I guess calculus-wise, it's slightly more difficult, but organizing the term might be easier. So there's no pros and cons.
Nice.
All right. Okay, so that's for the equation of state. And now we're ready to move to chapter 2.
Actually, I have a quick question.
Sure.
So we went through this whole derivation to find alpha. So
Yes.
alpha is different for every equation of state.
Yes, so if you think about it, what is alpha and chi? So these two are the partial differential equations, or these are actual experiments that scientists go and do, and they get an expression. So you can imagine like doing it backwards, is experimentally find like alpha and chi, and then derive the equation of state. But that's more complicated, and I'm not going to cover that. All right, so that's about it for chapter 1. Remember, chapter 1 is a basic introduction to terms in thermodynamics, calculus review, and equation of state. And now we're ready to talk about our chapter 2. Let's see where we are. All right. So in chapter 2, we start to talk about laws of thermodynamics. So in this lecture, we'll introduce some of the very important terms in thermodynamics, namely the heat and work. So these are the two line integrals that are very important in thermodynamics. On Friday, Dr. Wu will introduce you to our first state function, which is enthalpy, and also the first law of thermodynamics. And then we'll come up and talk more about how to calculate enthalpy, what exactly does it mean, and enthalpy and ideal gas law, and etc. So today we'll spend time looking at reviews on classical mechanics and make sure we're on the same page when we're talking about the physics behind classical mechanics. And then we'll talk about PV work and also heat. All right, so getting started. First thing first, classical mechanics. So in physics, when we're talking about classical mechanics, keep in mind that classical mechanics is laws of motion of macroscopic bodies whose speeds are small compared to the speed of light. So it's only applicable to macroscopic bodies. So like an electron, you should not use the classical mechanics. Or something that's moving super fast, you should not use classical mechanics. But for thermodynamics, in most cases, classical mechanics is good enough for our application. All right. And, well, at the heart of classical mechanics, we have Newton's law. So that's a quick physics review. When we're talking about force, it's a vector, and it's the mass times acceleration, which also is directional. And then when we talk about velocity, we have velocity as the first differential equation of your movement in space over time, where acceleration is the second derivative of the movement in space over time. What's more important for us is work. So when we're talking about work, which abbreviated as a small letter w, so dw equals to fx times dx. So that's a one-dimensional work when we're talking about it. Or a force, F, acts on a body, while the body undergoes an infinitesimal displacement dx in that x direction gives you the work. So that's the definition of work. Right, or if you're doing a definite integral, it can actually solve for a number of the amount of work done. And if you think about this one, now this is an integral, so work itself is defined for a process. Right, so if I'm pointing to an object that's not moving or not changing its state, like just pointing to this screen here. Now, you cannot say the work of this screen right now at this moment is like what number. It's not defined. So work itself is defined for a process. Or more specifically, if we look at the mechanical energy, the work energy theorem, what we can say is the work done on the particle by the force acting on it will equals the change in kinetic energy of the particle. Right, so work itself describes the change of kinetic energy on that particle. So that's the work energy theorem. If we look at a specific example, and imagine we have a force, some kind of vector force acting on a particle in three different directions. You have fx, fy, and fz using a Cartesian coordinate. And, well, let's say if fx equals to max, what does that mean? You can further write it as m dvx over dt, so that's acceleration. And then that also equals to m dvx over dx and dx over dt, because dx and dx cancel out, you get dvx over dt. And in here, as we were saying, we know that the dx over dt along the x direction, that's just my velocity along the way. So we can further simplify this fx to be m vx dvx dx. All right, and plug in this mvx dvx dx back into this original equation. We end up getting my work equals to, well, vx1, vx2, mvx dvx. Right, so your dx and dx will cancel out with each other. And the same applies to other directions. And solving these integration, now it's pretty straightforward. It's just vx dvx. You can solve that integration, and you can get the first integral to be 1/2 m times vx2 square minus vx1 square. And the same applies to 1/2 m vy squared 2 square minus vy1 square plus 1/2 m vz2 square minus vz1 square. Or just a change of kinetic energy in general, right? So you can take all the 2 out to be 1/2 m times vx2 square plus vy2 square plus vz2 square minus 1/2 m vx1 square plus vy1 square plus vz1 square. So the left one being your final kinetic energy, the first one being your initial kinetic energy. So this is a quick derivation on what do we mean by when we say work energy theorem. Or the other way to put it is we see the kinetic energy of the particle, or big K, as 1/2 mv squared. So your work for the process will be kinetic energy final minus kinetic energy initial for this one particle system. Right, so that's what we mean when we say the work itself describes the change of kinetic energy for this one particle system. So again, the take-home message is work is only defined when we're talking about a process. We're going from state 1 to state 2. All right. And then in mechanical energy, on top of kinetic energy, we also have a different kind of energy, which is potential energy. We will be using potential energy in this course, but in a much less degree. But I still want to mention, like, what is potential energy, right? So basically a potential energy, which we normally write it as a big V, as a function of x, y, and z, it's just a partial differential. It's just a differential of that potential energy to a certain direction, like dx, that gives you the negative of the force. So that's just a definition of potential energy. And in classical mechanics, we have conservation of all the mechanical energy, or the total energy of your kinetic plus potential energy will always be conserved, as long as only conservative forces are at. All right, so this part is just a quick review on classical mechanics. And then this one is just a sample question on unit conversion. So just make sure you know how to do it. It's pretty straightforward. I posted the answer to this practice problem on our annotated notes, so you can try it yourself. All right, so that's a quick review on classical mechanics. And now let's move on to talk a little bit more about work, more specifically PV work. There are different types of work. So PV work is normally when you're actually moving the, like say a pistol, and you're changing the size of your system. That's kind of work. You can also have electronic work. You can also have other types of work, or we call it non-PV work. We probably don't have time to talk about electrochemistry, but just recognize there's like PV work and non-PV work. Both of them exist. So for now, let's just focus on PV work. And when we're talking about PV work, in thermodynamics, we care more at the moment. Let's only talk about reversible processes. Later on, we'll talk about irreversible processes. But here is our first encounter of the definition of reversibility. So I want to read this slowly and make sure you know when we're talking about reversible system, we're saying a reversible system is always infinitesimally close to equilibrium. Any infinitesimal changes in conditions will restore both the system and surrounding to their initial states. Or the other way to put it in your textbook, you'll see like when we're saying a process is very slow, or something is moving at a very slow rate, that's normally saying like this, we're talking about a reversible system. All right. Or if you think about a chemical reaction taking place in a test tube, right? So at the surface of the test tube, when the reaction is taking place, your liquid in the test tube may be expanding or contracting slightly due to the chemical reaction. But because that expansion or contraction is taking place at such a slow rate, we can consider that process mechanically reversible. All right, so whenever something is like going like super small, super slowly, and it's more or less hinting a reversible process. Now, when we have a reversible process, what else can we do? We will have a way to solve for the work that's being done for that reversible process, or the PV work that's being done. So if we imagine a simplistic system, right? So like in here, you can imagine in the system, we have some kind of gas, like a cylinder of gas in there. We're applying force to push the piston so that the system is being contracted at a very slow rate. Right, so if in this case, we can think about first of all, the Fx and the change of the movement direction. They're in the same direction. So we're doing work on the system, right? So the volume of the system will decrease along the side. And in this process, using Newton's law, we have dW equals to Fx dx. And in here, we know that pressure, or Px in the direction, equals to Fx divided by area. Right, so this part is the overall area. So we can rewrite my dW equals to Pxa. So Fx equals to Pxa dx. And since our volume, or change of volume dV equals to minus A dx, right, so when my dx is moving to the right, the volume decreases. We can rewrite my dW reversible equals to negative Px dB for this closed system and reversible. Or in general, in this class, when we're talking about reversible PV work, we can write the following expression, which is the work reversible equals to the integral of your volume change between V1 to V2 negative PdV. All right, so both of these writings are correct for reversible work. So again, this fits our expectation of, remember that work itself is a path-dependent function. We're talking about how do we get from A to B. So the actual path of getting from initial to final state matters. So let's look at an example and see what exactly do we mean when we say work is a path-dependent function. Again, like whenever I'm drawing on the board, you can also see those drawings on our annotated note. So like, you should be able to have access to it. It just, if you're only looking at the recording, I won't be able to record the board. That's unfortunate. So, let's imagine two different systems. All right. So let's say, imagine we're talking about reversible PV work in a closed system. And let's imagine two different scenarios. So scenario one, we're doing the isochoric process followed by isobaric process. Right, so remember we went over these vocabularies. What is isochoric? The isochoric saying our volume is constant for our first step. And then isobaric, so this one is, something else is constant. Pressure is constant. Right, so if we're thinking about this process, what does it look like? Now if I put my P, my pressure as my y-axis, volume as my x-axis. And we start from a random point here, just my initial point. And let's say we do my constant volume process, so we'll decrease to my intermediate state, and then do a constant pressure process. So this is my A, and this is my B, to get my final point. Right. And if you think about, if we're doing the integration on my PV diagram to find out the work that's being done going from initial to pressure, to final, that's gonna be the area below this curve here. All right. So what if I want to get to my initial to final point, but now following the reverse process? Let's say we first do an isobaric process, then a isochoric. So what does that look like? So it's the same PV diagram. I want to start from the same initial and final process. But in this case, we're doing our isobaric expansion first. So we go from here, that's my A prime, and then my B prime, which is the isochoric pressure change. Now below the curve, the area or the work that's being done will be different. All right, so this is what we mean when we say work itself is a path-dependent function, meaning like depending on what path you're taking, you end up doing different amount of work on the system. With me so far? All right, so this is one of the common misunderstandings is whenever we're talking about work, or later on also heat, is also always keep in mind work itself describes a process from your initial to final state. Depending on what kind of path you take, you might experience, or the system will have different amount of work that's being done. So pay attention to the actual path going from initial to final state. Or the other way to put it, like in a true or false problem, I would say, given the initial pressure and volume, and the final pressure and volume, you can always calculate the amount of work that's being done. Is that true or false? So it's false, right? Because you need to define the path in order to calculate the PV work that's being done. And the other example question we might have is to actually calculate numeric numbers, right? So this is the example question we have. You can read it together. See, a non-ideal gas is heated slowly and expands reversibly at a constant pressure of 275 torr from a volume of 385 cubic centimeter to 875 cubic centimeter, and find out work in joules. So this one, the way to read it, we see, okay, so the gas expands reversibly. Because it is expanding reversibly, we can use our D reversible, dW reversible equals to negative PdV. And then in here, we also read my pressure is constant. So I know my pressure is constant. And then just a simple math problem, plug in the numbers. You do the integration on both ends. You get W reversible equals to negative V1 to V2 PdV. Or since my pressure is constant, it's just negative P times V2 minus V1. Right? You can easily imagine, like, instead of giving you a constant pressure, we can say this is an ideal gas. And then likewise, you have a way to solve for the relationship between pressure and volume. But in here, we know that pressure is constant. And then just plug in numbers, right? So negative 275 torr times 875 minus 385 cubic centimeter. And that gives you negative 1.35 times 10 to the fifth torr cubic centimeter. You can do the energy conversion or unit conversion to 18.0 joule. And if unit conversion is needed, I'll make sure to tell you like how to convert between like torr centimeter cube to joule or something. Just you're responsible to know what number to plug in. I might give you like 5 different units, so you can just play around with them. All right, so that's the work part. Any questions before we move on to talk about heat? Nope, we're all good. Okay, sounds good. Next one, heat. So, like work, heat itself is one of the things that we use a lot, but we want to give it a more careful definition in thermodynamics so that we're making sure talking about the same thing. So again, using our milk example, right? Imagine I have my temperature of the milk to be 25 degrees Celsius, the temperature of the cooler initially to be 4 degrees Celsius, and I might put my bottle of milk into my cooler, take it enough time so that both the temperature and the cooler will end up to be the same temperature after a given amount of time, right? When they reach thermal equilibrium with each other. So in this process, we say there is a heat transfer taking place between the milk and the cooler. All right, so the heat is going from an object that's at higher temperature to the object with lower temperature. So in this case, the milk is transferring heat to the cooler, and the cooler is accepting heat from the milk. And the amount of the heat being transferred between the milk and the cooler will add up to be the same to each other, assuming the cooler itself is adiabatic. It doesn't exchange heat with the surrounding. Or in this case, we say that heat will be equal to M2C2, so mass here is the mass of, say, cooler. Wait, this one is milk because it's higher in temperature. And C2 is the specific heat of milk. T2 is the initial, like 25 degrees Celsius, and my T final is 4.1 degrees Celsius. And that's the amount of energy transferred from the hot cup of milk to the cooler. And on the other hand, the cooler is accepting heat, right? So this is the mass of the cooler. My C1 is a specific heat of the cooler. My T final is again 4.1. My T1 is 4.0. We'll talk more about heat capacity, but in this equation, that small c is a specific heat capacity. It's more or less like an average heat capacity that scientists can measure. Later on, we'll give heat capacity a more careful definition in terms of thermodynamics. But for now, the heat capacity is something you can measure. And it can be a function of pressure and temperature as well. So as we can see in here, my heat itself, like work, is only defined for a process where heat transfer is taking place. All right, so it's like I cannot point to, say, the screen and say, hey, the work of the screen is like 2 joules. It doesn't make any sense. The work is more like associated with like I'm moving it, right? So there's work associated with the movement. So heat is the same idea. I cannot point to just like the screen and say, hey, the heat of the screen is like 2 joules. It doesn't make any sense. It's more like when I'm touching it, there's like heat transfer from my hand to the screen. And we can talk about heat being the amount of energy transferred in that process. Yes?
So it's not like there's a heat of the milk and heat of the cooler. It's like there has to be a heat transfer
Yes.
between the two.
You can talk about temperature of the milk and temperature of the cooler being different. And because of that temperature difference, there's like energy, thermal energy flow between the milk and the cooler. And that flow of thermal energy, that's what we call heat. All right, so it's only describing a process. All right, yes.
I was just wondering about like see how like it's like titled as like specific heat capacity. But like is it like a specific heat capacity in terms of like the environment that is put in? Because like let's say we were put in like the milk in the freezer, then like its capacity would get like.
Right, so I guess the way to put it is we have different mass and you have the change of temperature. So these specific heat capacity is something you can experimentally measure, right? So obviously C2 and C1, they're related to each other, right? Because the amount of heat we give in and the amount of heat accepted, they are related to each other. Now, what is that relation? That's experimentally determined. So later on, we'll have more sophisticated discussion on heat capacities and so on. So right now, I just want to use this like a easy example to introduce the idea of heat being a process-dependent quantity, right? You should never point to something like, say, the heat of this chair is blah, blah. It doesn't make any sense. And to give it a more general description in what we just described for the milk example, we can say the change or the infinitesimal amount of heat transferred at constant pressure equals to mass times the specific heat of that compound and dt. All right, so in here, the first term, this one is the infinitesimal amount of heat. M is mass. Cp, that's the specific heat at constant pressure. So whenever you see like little subscription next to heat or next to like heat capacity, we're saying these are the terms at constant pressure. We'll see that more often later on. And then dt, that's the infinitesimal change of temperature. All right. And for chapter 2, like what we did with work, I expect you to know how to plug in numbers and to solve for numeric answers for the heat amount, for the amount of heat that's being transferred, or calculate the specific heat of, say, a metal. So like if we read this one together, we can say that specific heats can be measured in a drop calorimeter. here a heated sample is dropped into the calorimeter and the final temperature is measured. So when 45 grams of a certain metal at 70 degrees Celsius is added to 24 grams of water, and we know the specific heat capacity of water is given to be 1.00 calorie per gram per degree Celsius at 10 degrees Celsius. So the water is at 10 degrees Celsius in an insulated container. The final temperature we measured is 20 degrees Celsius. The question asks you to find the specific heat capacity of the metal based on this experimental observation, and then calculate how much heat flow from the metal to the water. Right, so this is a kind of experiment we were just mentioning about the heat capacity is related. So in this case, what we're doing is calculating, well, mass of the metal times the heat capacity of the metal times the temperature of the metal minus the temperature of the final mixture. And this must equals to mass of water times the specific heat of water times the T final minus the T H2O. Right, and do we know these numbers? Well, the mass of the metal, that's 45 grams. The specific heat of metal, that's something we're trying to solve. The temperature of the metal, this one is, the temperature of the metal is 70 degrees Celsius. The final temperature is 20 degrees Celsius. Mass of the water is 24 grams. And then we have, well, the heat capacity of water, that's 1.00 calorie per gram per degree Celsius. The final temperature is 20 degrees. Initial temperature is 10 degrees. Right, it's basically just finding these numbers and plugging the numbers. And now let's look at this equation. Well, the only thing unknown is what we're looking for, the specific heat of the metal. And we can solve for a numeric answer here. Right. And the amount of heat transferred is just everything taking product to each other. Yes?
To not get confused about which object we put on the left-hand side and the right-hand side, should we think about it as what's causing this certain object to get a change or a reaction?
I think the best way to answer that question, where to put on the left and what to put on the right, well, you always keep your, one of them is system, the other is surrounding, right? So in this case, the system, I'm taking the system as my metal, the water being my surrounding, right? So the system works on the surrounding, or the system transfers heat to the surrounding, right? So always keep everything of the same nature on the left and then the same nature on the right.
Wouldn't it be the opposite where the surrounding is causing heat in the system?
It doesn't matter, you can put it on the right as well.
I see.
All right. So yeah, here is a quick introduction into, again, review on classical mechanics. We then introduce two very important line integrals, meaning they are both path dependent, right? Both work and heat, they're defined for a given process, right? So work, we're talking about mechanical work with pressure and volume. Again, it's describing I'm physically moving something, right? So that's a PV work. And then heat is the same idea. It's defined for a process only. All right, so these two are the line integrals. And in the next lecture, Dr. Wu will introduce your first law of thermodynamics and also see your first state function, enthalpy. And we'll come back next week and see the application of the first law of thermodynamics. Okay, that's all from me today. And also, by the way, if you are here and you don't have access to our lecture note, send me an email with your UID so I can add you in so you're not missing anything. All right, that's all from me.